Welcome to this video in the Matter unit. In today's video, we are going to explore properties and change. Following this lesson, you guys are going to be able to differentiate intensive and extensive properties, define physical and chemical properties, and certainly differentiate them given examples, and also identify and distinguish between physical or chemical changes. If you have not already done so, make sure you have your chemistry binder handy so you can take notes on the content and the examples that are in this video. So without any further ado, let's get cooking. Properties are a super important thing for a chemist to know. When I was a research scientist, it was really important that I understood the properties of the chemicals and the reagents that I was working with because they allowed me to make lots of choices as far as what I was going to do with them and the reactions that I intended to create. So the way you can think about properties is a little bit the way you think of character traits in your English language arts class. Whereas character traits describe characters, properties are essentially your character traits or your characteristics of matter. And as I said before, any chemist is using these characteristic properties of matter all the time to propel their work. What do we do with those? Well, properties are really nice to distinguish between different substances because if you know the properties of something, you can do a little detective work and see what substance matches those. They're also nice to characterize or classify different substances. For instance, we know the properties of metals, and if something exhibits those properties, it falls into that category. And of course, as I said before, there is usability. You want to make sure that if something is flammable, you don't use it to put out a fire. So there are two types of properties that you probably already know about from other science classes. They are your physical and chemical properties. So let's dive into physical properties first. Now, physical properties are observed and described mostly through the use of the five senses, whether it's looking at the basketball and saying the basketball is orange, or the football is brown, or oblong, or the tennis ball smells like rubber, or the hockey puck is hard. We used our five senses to make all those qualitative observations. Another way physical properties are observed and determined is using measuring tools. Measuring tools are any instrument in the lab that we can use that gives us quantitative data. So whether we're talking about a thermometer, or we are talking about the mass of gold that's here, or we are talking about the length of a shoe print, any one of those pieces of data are describing physical properties. So we used our five senses along with the measuring tool to make those observations that are numerical at their core. In both cases, what is unique about physical properties is after the observation of the substance is made, that substance will always retain its chemical composition as it was before you observed that property or made the measurement. The composition does not change. Before we move on, I want to caution you guys about melting points and boiling points. They are indeed physical properties, even though a lot of people think that they are chemical properties. And here is why the melting point and boiling point are physical. In order to truly understand it, you need to think about what is happening on a particle level. When solid iron is melted at about 1538 degrees Celsius, the arrangement of the iron atoms looks like this, but then quickly changes from a crystalline lattice that's solid to this mishmash of iron atoms that are now in the liquid state. They are red iron atoms as a solid. They continue to be red iron atoms as a liquid. No compositional change occurs when you take that melting point observation. Only the arrangement, which is how we determine our phases, changes. So we will say that because the composition doesn't change, the property that we just observed is a physical property. So another reason to not be that guy. Make sure you tuck that in your memory banks. Let's now take physical properties a little bit deeper. Physical properties fall into two categories. They are extensive and intensive properties. By definition, extensive properties are properties that will depend on the amount or extent of the matter that is in the sample. Extent, extensive. So for instance, the property of mass. That is a property that will change depending on how many atoms you have. If you have something that has a lot of atoms in it, it will be massive and have a great mass, a very high mass. But if there's not a lot of particles that are there, the amount of particles is few, the mass will be very small. Same with volume, same with caloric intake, or anything that the property changes when you simply add more of the matter. Intensive properties depend on the type of matter you have and not the amount present. Thinking about earth science, you measured a lot of things on your hardness scale. Well, something like talc that's not very hard at all doesn't change whether or not I have 10 grams of it, 100 grams, or 1,000. Diamonds, super hard. Those are 10 on that Mohs scale. And it doesn't matter whether I have, a giant 4-carat diamond or I have a tiny little 2-carat diamond, which still, for you guys playing along at home, is pretty big. Density is another such property that's intensive. Remember, density is a linear relationship. It is the ratio of mass over volume. So as your sample grows in mass, it's going to grow in volume as well. And that is why density is a nice identifying property to determine the identity of matter. Here are a bunch of intensive and extensive properties for you to write down for examples in case you are ever asked for one. So right now we have cleaned up the right side of this flow chart. We've started with general properties of matter. We are gone through the physical aspects of them and then now talked about intensive versus extensive properties. It is time to go make our way to the left side of the flow chart. The left side of the flow chart is all about chemical properties. And chemical properties are properties that are observed when there is a change in the composition of your substance. So note to self, in order to see a chemical property, you must have a chemical reaction that is occurring. Take a look at this old car that's sitting out in the field. Well, it's rusting. Rusting is a chemical property of iron. And we only see this property of iron when iron is combining with oxygen gas to make a new substance which is called iron 3 oxide. Here is the skeleton of that reaction, which is here. It is not a balanced equation yet because you guys aren't quite ready to do that, but you will very soon. Another example of a chemical property is that copper will oxidize when exposed to oxygen. Now, we would have no idea that this happens unless we saw the result of that. And of course, you're looking at this right now going, hey, wait a second, that Statue of Liberty is nice and brown like a brand new penny when we are used to the Statue of Liberty looking like this. This green patina that you see here is copper oxide, and that is the result of a reaction between copper and oxygen gas. We would never know that copper oxidizes like that unless we witnessed the chemical reaction. So that was all about its behavior. So in summation, chemical properties essentially describe potential to undergo a chemical change of some kind, a reaction, in the presence of other substances or energy. It describes behavior. So examples of that, other than the two that we did, zinc has the potential to react vigorously in hydrochloric acid. Gasoline is flammable, whereas a chemical property of apple juice, and this is interesting because you can negate some chemical properties, is that it is not flammable. Remember, it describes behavior. It does not undergo a combustion reaction when you drop a match in it. Baking soda creates a colorless gas called carbon dioxide when mixed with vinegar. We don't know that unless we're witnessing the behavior. The second part of this video is all about changes in matter. So we are going to segue from physical and chemical properties now to physical and chemical changes. And for the introductory chem student, this is often hard to keep straight whether something is a property or a change. So I'm going to do my best to clean it up for you guys and make it palatable and digestible. Change in matter. Well, the simplest I can put it is that matter can change in its appearance, which is known as a physical change, or it can change in its composition or identity. That is known as a chemical change. So you have to think when we are talking about what kind of change we are observing is whether it was just a change in appearance or did we have a chemical reaction and change the identity. A great way to illustrate the difference between the physical and the chemical change is through these examples that we see here. One of these changes is physical and one of them is chemical. And what you must remember is that physical changes change the appearance of something, the arrangement of something, and a chemical change will change the chemical composition or identity. What we have to do is look at what's happening on the left side versus the right side. And here I can see I have a particle that is a blue circle bonded to a white circle. Well, this is my reactants that are here, and I'm noticing in my products I still have a blue circle and a white circle. So it looks to me like the identity did not change here. Looking at this bottom one, we started with the blue and the white circle, but in my product side over here, it looks like now I have a diatomic double white and a diatomic double blue. If we were to think about this critically, the top example was the physical change where only the appearance of the particles has shifted or changed. And in the bottom, we have the chemical change where the identity or the composition changed. We cease to be the blue and the white circle, and we have gone to the diatomic whites and the diatomic blues. Let's say we were to heat up some ice and we were to take it to its melting point and melt it and turn the ice, which is H2O solid, into H2O liquid. And then we were to heat it even further and turn it into H2O, you guessed it, gas. Would this be a physical change or chemical? Well, one of the things you have to consider is the identity of the particle in all of these cases was an H2O molecule. So what we're seeing is ice is H2O. Water is H2O in its liquid state. Gas is still H2O. The identity stays the same here, so this was a physical change. So the big takeaway is phase changes are always physical changes, and you will remember that because there's a P here for phase change. There's also a P in physical change. So another good thing to make a star next to in your notes so you don't forget it. When asked questions about physical changes, there are often some key vocabulary words that you may see that indicate a physical change has occurred. Melting, breaking, splitting, shaving, crushing, ripping, cracking, all kinds of stuff like that indicate a physical change where we are simply changing the shape or the size or the appearance of something, but not changing its composition. So the big takeaway to remember is this: after any physical change is made, you will never alter the composition of the substance, meaning that your substance will be identical to what it was and will retain all the properties that it had before the physical change occurred. The reason it retains all that properties is because the composition stays the same. The last noteworthy nugget that I want to throw at you guys involves dissolving solids. Whenever we dissolve something, the change is physical. Now, you may be saying, well, wait a minute, did we not just fundamentally change the identity of our substance? And, well, the answer is no, we did not. When you take water and you drop salt in it, all the water is doing is breaking this crystal lattice up here and hydrating the ions. The ions are being picked up by the water, carried into solution, and all we are doing is changing the appearance of our sodium chloride. Another cool thing about this is if I really wanted to, I could get the sodium chloride back so we didn't make something new at all. How would I do that? Well, pretty simple. We would have to evaporate off all the water and we would be left with the original solute that we had. So that is why this change is physical and not chemical. Let's finish up this video and now talk about chemical changes. Chemical changes occur when a substance will combine with something else to form a new substance. And in order for that to happen, you guys need a chemical reaction, which is super important. Anytime you have a chemical reaction, you are changing the composition of what you had and turning it into something new. Check out this example. Here I have two reactions. The first one is the Haber process where we make ammonia. Ammonia is NH3. You guys need to remember that. And What's cool about it is nitrogen gas goes in, hydrogen gas goes in, but what comes out is NH3. We have changed the composition from the reactants to the products and made something new. Same with this here. Here I have sodium hydroxide, which is a strong base. Here I have hydrochloric acid, which is a strong acid. But when you mix them together and a chemical reaction ensues, you know what you get? You get salt water. And last I looked, we go swimming in that. We get it in our eyes. Some people soak their feet in it, and it's okay. I would not recommend doing that with sodium hydroxide or hydrochloric acid. So a takeaway here is that when we do initiate a chemical change, not only do we change the composition and get new products, but the properties of those products now change as well. And they are not the same as the properties of the reactants that we had. So that is a super important thing to understand. We cannot undo these chemical changes unless we have a chemical reaction to do so. Such as if I wanted to separate the sodium chloride, I could do so using electrolysis, but that would require a chemical reaction. I can't do it by any physical means. So guys, that's it for us. If there was anything that is vexing you on physical and chemical properties or physical and chemical changes, make sure you bring those questions to the Burning Questions segment during the next time we convene as a class. That's it for me. I will see everybody on the flip side. It's been a pleasure taking you through this lesson. Peace out.
That's all, folks.